All right, welcome to The Explainer. Today, we're diving into a really cool puzzle. It's one that connects two worlds you probably wouldn't think belong together: artificial intelligence and, well, the evolution of life itself. And the key that unlocks it all? It's this single, powerful idea that's going to change how you look at both. I mean, really, stop and think about that for a second. What on earth could an AI chatbot, something like Grok 3, which is just code and data, what could that possibly have in common with the messy, beautiful, sprawling story of biological evolution? It sounds like two completely different universes, right?
Well, it turns out the answer isn't some, fuzzy philosophical concept. Our source material for this explainer from LF Yada points to something much more concrete. It's a real, measurable idea from physics and information theory, and it's the rulebook that both of these incredibly complex systems follow.
And that concept is entropy. Now, you've probably heard this word before, right? It's usually talked about as chaos or randomness or the tendency for things to just fall apart. And that's exactly it. In both AI and in life, the name of the game is this constant battle against entropy. It's a never-ending struggle to create order from all that randomness. So, let's break this down. We're going to look at these two worlds, AI and life, and see how this one rule, this fight against disorder, plays out in both. First up, let's tackle pillar one. We'll start in the world of AI, specifically with large language models, or LLMs. So how exactly do they fight this battle against uncertainty?
Okay, so at its very core, an LLM's entire job is to reduce uncertainty. It looks at a bunch of words and then has to predict what's coming next. It's basically an uncertainty-crushing machine. You give it the cat sat on the, and AI's goal is to sift through the chaos of every possible word in the universe and narrow it down to the most likely one, which is probably math.
So how does it do that? Well, the main tool it uses is something called cross-entropy loss. Now that sounds technical, but you can just think of it as a surprise-o-meter. During training, every time the AI guesses the next word and gets it wrong, that meter goes way up. It's surprised. The whole point of the training process is to tweak its own internal brain again and again to get that surprise level as low as possible. It's learning to be less surprised by the right answer. But here's where it gets really interesting. If an AI only ever gave the most boring, predictable answer, it would be pretty useless, right? Super rigid. So the people building these things have to do this delicate balancing act. On one side, they want low entropy, safe, accurate predictions. But on the other, they need some high entropy. They actually inject a little bit of controlled chaos, using tricks like temperature scaling to encourage the AI to be more creative and explore different, less obvious paths. It's this constant trade-off between being correct and being creative. Okay, now let's pivot to our second pillar, life itself. And as we go through this, you're going to see an almost spooky parallel here, because life, just like AI, is in a constant fight to pull order out of chaos. Think about it. From a single tiny cell all the way up to us, biological systems are constantly pushing back against the universe's default setting, which is disorder. They are working 24/7 to beat back that internal randomness so they can build and maintain the stable, functioning structures they need to, live. And life has its own incredible tools for this job. You can think of them as cellular managers. You've got things called transcription factors. These are basically proteins that act like tiny, precise light switches, flipping specific genes on or off to make sure a cell is doing exactly what it's supposed to do, reducing all that randomness. Then you have epigenetic marks, which are like permanent sticky notes on your DNA. They create these super stable, low-entropy patterns that define what a cell becomes. It's what makes a muscle cell for its whole life, and not a brain cell. They are literally locking in order at the molecular level. And does this sound familiar? Biology is doing the exact same balancing act we just saw in AI. It desperately needs that low-entropy stability to make sure your heart cells keep beating like heart cells. But it also needs some high-entropy flexibility so it can adapt. When you get a cut or you're fighting off a virus, your body has to be able to change things up, to fire up different genes to respond to that new stress. It's stability versus adaptability all over again. Okay, so we've got these two systems, AI and life, and they're both managing entropy in this really similar way. But what's the real connection? Where's the bridge? Well, this is where the source material we're looking at builds a truly fascinating argument. This quote from LF Yada really nails it. The key insight is to stop thinking of AI as something we just build and to start seeing our own actions, the data we choose, the feedback we give, as the environment that the AI is evolving within. We are the environmental force. Let's just break this parallel down because it's so powerful. In nature, the environment is all about ecological pressures, right? A desert, a rainforest. For an AI, its environment is the massive, curated dataset we feed it and the feedback we give it. In evolution, selection is all about survival of the fittest. For an AI, selection is us. It's our design choices and our decision about which models perform better and get to live on. And the result in both cases? Adaptation. In nature, you get organisms that are more fit for their environment. In AI, you get models that are more accurate and specialized for their tasks. Let's make this super concrete. The data we feed in AI, that's its ecological niche. It defines the world it knows. The architectural choices we make, like switching to more efficient designs like transformers, that's a selective pressure we're applying. And maybe the most direct parallel, when we use things like reinforcement learning from human feedback, or RLHF, we are literally acting like Mother Nature. We are actively rewarding the AI behaviors we like and punishing the ones we don't. That is selection. So, looking at ourselves as the environment for AI isn't just a neat little analogy. It's a really powerful new way to think. And it raises a big question. If this is an evolutionary path, where is it leading?
Now, look, we have to be intellectually honest here. As our source material points out, this parallel isn't perfect. It has some pretty important limits. We can't just say AI evolution is identical to biological evolution.
And here are the big ones. AI evolution is directed. We're pushing it towards specific goals. Nature's evolution, it's completely undirected, totally open-ended. The timescale is also just wildly different. AI evolves over months or years. Life takes millions of years over countless generations. And obviously, AI doesn't reproduce by itself. We're the ones who manually copy and improve the code. But even with those big differences, the core insight is still incredibly powerful. This whole framework of seeing our own influence as an environmental pressure, it forces us to take a whole new level of responsibility for the evolutionary track we're putting these systems on. We're not just engineers. We are, in a sense, the gardeners in this new digital ecosystem. And that leaves us with one final, really big question to chew on. If we are the environment shaping AI's evolution, if we are the selective pressure, if we are the force of nature in this new world, then we have to ask ourselves, what exactly are we evolving it into?